Okay, so yesterday we talked about our sun. Today we're going to talk about other stars, okay? Properties of stars, patterns that we see among stars, and then finally talk about star clusters and how there's two types of star clusters. So how do we measure how bright stars are? Stellar luminosity. So luminosity is the amount of power a star radiates, its energy per second, also known as watts. And the apparent brightness is the amount of sunlight that reaches Earth, so energy per second per square meter. So luminosity is dependent on two things: how far away the star is, as well as its luminosity. Okay, question for you. Alpha Centauri and the Sun have about the same luminosity. Which one appears brighter? I hope you say the Sun, because of distance-wise. The Sun is closer to us than Alpha Centauri. All right, so the amount of luminosity that passes through each sphere as it's traveling is the same. So you can figure this out by looking at the area of a sphere, 4 pi r squared, divide the luminosity by the area to get its brightness. Now, we're not going to do any math, and in fact, I'm probably not even going to quiz you on the amount of luminosity on different stars, but I just wanted to introduce it to you. So the relationship between apparent brightness and luminosity depends on its distance. Okay, so luminosity divided by 4 pi, and then distance squared. We can also determine the star's luminosity if we measure its distance and apparent brightness. You can rearrange the equation to solve for luminosity. So, question for you: what would the apparent brightness of Alpha Centauri change if it were 3 times farther away? So, 3 times farther away. So if I stick a 3 here, 3 squared is 9, and then because it's inverse, it would be 1/9 as bright. So your option is C. Now, how do we measure how far away stars are from us? We use parallax. We've talked about parallax earlier in the semester, but it's the apparent shift in position of a nearby object. You use parallax to find your dominant eye if you've ever taken gun safety training. So in astronomy, as we're traveling around the sun, we study stars or groups of stars in the sky. And so in January, we would see this pattern. But then in July, on the other side, we would see this pattern. And so we can measure the apparent shift of objects through parallax to figure out how far the object really is. Now we can also measure stellar temperatures. So remember, every object gives off thermal radiation, and it depends on its temperature. And so if an object of fixed size grows more luminous, that means its temperature is increasing. So some properties of thermal radiation we should be aware of: hotter objects emit more light per unit area at all frequencies, and hotter objects emit photons with a higher average energy, and both those just make sense. Now, because of temperature, as you increase in temperature, we can have different levels of ionization occur, and use absorption lines to tell us what level of ionization it is at. So that's kind of cool. Now, lines in a star spectrum correspond to spectral type, and it does reveal its temperature. So we have classifications of stars that we might call O, B, A, F, G, K, or M. And O is the hottest, and M is the coolest. And so a mnemonic device to help you remember, you can say, "Oh, be a fine girl, kiss me," or maybe this one: "Only boys except in feminism get kissed meaningfully." So what kind of star is hottest? So if you look over here, O, B, A, F, G, K, M. O, B, so it would be A, right? Yep, okay, A. Pioneers of stellar classification. Who do we have to thank? Annie Jump Cannon and the calculators. All of these fine women and gentlemen at Harvard laid down the foundation for modern stellar classification that we use today. Okay, we can also measure stellar masses, but we can only do it in stars that are in a binary star system. And the reason for that is the strength of gravity is associated with it. Now, there are 3 types of binary star systems, and about half of all stars that we see in the sky are actually in binary star systems, and ours is not. So it's kind of interesting there. But there are 3 types: visual, spectroscopic, and eclipsing binary. But like I said, the only way we can really measure mass of a stellar or a star, distant star, is if it's in a binary system. So visual binary means that we can directly observe the orbital motions of these stars. So here's A and B, and you can kind of see that these objects are going around each other. Spectroscopic binary means we're measuring the Doppler shifts of objects as they move. So red shift versus blue shifts. And then eclipsing binary is that we just measure how often they eclipse each other. Patterns among stars. So your assignment tomorrow, you're going to be dealing with a Hertzsprung-Russell diagram. And this diagram basically plots luminosity on the vertical axes and temperature on the horizontal. And you can kind of see also the classification of stars here. Okay. Now, these stars right here, you can see that they have been named, and these are called main sequence stars. And I'm trying to find our sun. Our sun should be somewhere right around here, but I'm not seeing the name of, it should just say the sun. Oh, there it is, right there. Boom, sun. Okay, so most stars fall along the main sequence. Okay, stars that have a lower temperature and higher luminosity are giants and supergiants. And stars that have the inverse of that, higher temperature with a lower luminosity, are called white dwarfs. Now, the HR diagram shows us a lot of information. It can tell us temperature, down here, color, spectral type, that's kind of listed on here, luminosity over here, as well as size, radius. So lots of information from just one diagram. So there are some luminosity classes that we should be aware of, and they are denoted by Roman numerals 1 through 5. 1 is a supergiant, 2 and 3 are some types of giants, or I guess 4 too, but then 5 is your main sequence. So our sun, G2V, so this means it's main sequence. And then remember, O, be a fine girl. So there's the G. And then I don't know exactly what these numbers represent. But if we go back here, here's G. And then it's 5, main sequence. And there's our sun. Okay, so which star is the hottest? You should say A. Okay. Which star is the most luminous? That's on the vertical axis. So, see? Yep. Sorry, I think I hear someone knocking on my door. Which star is a main sequence star? That would be D. Which star has the largest radius? That would be C. Okay, so the significance of the main sequence, these stars are fusing hydrogen into helium. Sorry, hold on. What?
Me.
Are you done? Where's Dad?
Over there. Where'd Dad go?
I don't know. Okay, come on in and close the door. Sorry, my daughter.
Sure, Mom.
Okay, make sure you take off your boots and your hat and your gloves and just put them on this chair for Daddy, okay? All right. So they fuse hydrogen into helium into the cores like the sun. Luminous main sequence stars are hot, denoted by the color blue, and less hot or cooler stars are yellow or red. And so mass measurements of main sequence stars can show that hot blue stars are much more massive, as you can see in the picture, than cool red ones. So, all right, another thing we should be aware of, core pressure and temperature of higher mass stars need to be larger in order to maintain that gravitational balance that we talked about yesterday. And if we have a higher core temperature, the fusion rate also increases, leading to a larger luminosity. So in review, we talked a little bit about luminosity, how it's determined from brightness and distance. We talked about temperature from color and spectral type, and you can kind of see the temperatures of stars vary. And then we have mass, which I didn't really talk about in depth because there's some math in there and I didn't really care for it. But you do need 2 stars or star in a binary system. Okay, mass and lifetime. So the sun's expectancy is about 10 billion years, and whenever we do comparisons to other stars, we tend to use the sun in some form. Shh, quiet. Until the core hydrogen is used up, at least 10% of it is used up. All right, so the life expectancy of a 10 mass sun star, so that means 10 times larger than the sun, means it's going to burn through its fuel much faster, and it's about 10 million years compared to our 10 billion years. The life expectancy of a sun or a star that is 0.1 the mass of our sun means that it's going to not go through its fuel as fast as our sun. It's 100 billion years compared to our 10 billion years. So high mass stars have high luminosities. They're short-lived, larger radiuses, and blue in color. Low mass stars have low luminosities. They live longer. They have a smaller radius and tend to be red or yellow in color. Now, stars that are off the main sequence, and this is where it gets kind of cool, are giants and supergiants. If it's above the main sequence, that means they're larger, redder, they go through their core of hydrogen a lot faster. Stars that are below the main sequence are smaller. They end up the color white after fusion has ceased, and we call them white dwarfs for a reason. So which star is most like our sun? You should say B. Which of these stars will have changed the least 10 billion years from now? That would be C, because it's a main sequence and it's conserving its energy. Which of these stars can be no more than 10 million years old? This one should be A. I'm just going to double check my key. Yep, because it's burning through its fuel a lot faster. Okay, so why do properties of stars vary? There are some stars that don't follow exactly main sequence supergiant or white dwarfs, and so any star that does vary significantly, we call them variable stars. And the reason for that is it's having a hard time finding the proper balance between gravity and pressure. And so the star will alternatively expand and contract in varying brightness to try to find that balance between the two forces. So a lot of times we see variable stars that pulsate, okay, where the apparent brightness will decrease and increase over a certain period, in this example, a 50-day period. A great example of a variable star is called the Cepheid variable stars. And a lot of times you see these variable stars in an area called the instability strip right here on this HR diagram. But the most luminous ones are the Cepheid variables. Okay, finally, we have star clusters. And there are two types: open clusters, where there's a few thousand loosely packed stars, and we have globular clusters, where we can have up to more than 1 million stars in a dense ball, and they're all held together by gravity. So we can measure the age of star clusters based on just comparison to other stars, but we know that massive blue stars will die first, followed by white. Then we have your yellow, orange, and red stars. The Pleiades now have no stars with no stars that have a life expectancy less than 100 million years old, and so we have the main sequence turn-off spot right here that can help us tell us the age of certain stars, and so we kind of have a nice little scale here. So as our sun goes through its aging process, it will no longer be yellow. Eventually, it will turn into red and get cooler and cooler in colors. So to determine the accurate ages, we compare models of stellar evolution to the cluster data that we collect. And we just know that the oldest globular clusters have revealed that they're about 13 billion years old, not far from the start of the Big Bang, which we'll talk about more later on, I should say, in the semester. Okay, so sorry about the disruption of my daughter. She just came back in from playing outside. But that concludes Chapter 15, Surveying the Stars. Tomorrow's a work day. You're going to get an HR diagram worksheet and a star worksheet. So it's a work day. It's due by midnight tomorrow night. And yeah, that's all you have to do. Make sure you guys submit your active notes. That counts as your attendance for today.